وصلتك؟ Short have been started. ممكن يطلع لك
Yeah,
هيك
looks
بار.
like.
اوكي، هيك نقطة حمراء في الأعلى.
Yes,
ايه،
yes.
تمام تمام تمام.
Okay.
ما أعرف دكتور
تمام.
محمد،
Okay.
احنا ناخذ من وقتك دقيقة ولا دقيقتين بس عشان just one
أسمعك
or
مستر ماز.
ايه تمام. So I would like to welcome everybody for our second webinar for 2024. This year theme will be focused on production logging. We plan to do 10 webinar this year. I'd like to welcome Mr. Samir Mostafa. He's the regional business development manager for MENA, Turkey, and India for Scientific Drilling International. Just I will share my screen for a second. Okay. Yes. Okay. My screen is clear. My screen is clear.
Yes, yes.
Yes. Okay. So this is our second webinar for this year. It will be in regards to high temperature and slim production logging tool from Scientific Drilling International. Will be presented by Mr. Samir Mostafa, Regional Manager Business Development for MENA and Turkey and India. As mentioned, we plan to do 10 webinars this year. Okay, this is our next webinar, one webinar per month. Next month, we will have Kappa, afterward Baker, Open Field, SLB, and so on. I would like to thank all our sponsors company for their time and dedication for sponsor this technical event. As we did last year, for the people that will manage to attend 6 of our webinar will get a special certificate. Last year, 2 of attendees managed to do so. Mr. Aus and Mr. Delvin. Okay, and if you like to join Iraq chapter, local chapter, that will be an honor for us. Okay, with no further ado, I will keep the mic for Dr. Mohammed. Okay.
Yes, Mr. Mazen. Hello, everybody. Hello, Mr. Samir Mostafa. Today is the 7th of April 2024. This is Muhammad Jawad Zainul Abidin, Vice President of Technology Society of Petrophysicists and Well Log Analysts, SPWLA Iraq chapter. SPWLA Iraq chapter would like to introduce today to you a free webinar. This is the second webinar, as Mr. Mazen said, regard to high temperature slim production logging tools by Scientific Drilling Company. Tools theory along with case studies to be presented by Mr. Samir Mostafa, who has a MSc degree in petroleum engineering. We wish you a distinguished time during the webinar. Mr. Mazen, mic with you.
Thank you all.
Thank
Mr.
you.
Sim, you can start the webinar.
Right. Shukran. Thank you, Mr. Mazen. Thank you, Dr. Muhammad, for the introduction. This is my second time here, so I would like to thank you for the opportunity, the SPWLA Iraq chapter, and also I'd like to thank all the attendees for investing their time to attend this presentation. It will be a quick one, so I will not fill the hour, hopefully. So I know it's Ramadan and you would like to do a lot of your regular stuff. So my name is Sabir Mustafa, and I will walk you through technical overview about our equipment and the tools, how we can address 3 main challenges in the production logging in our regular reservoir surveillance. We will talk about the slim MPLT, the high flow rate well intervention, and the high temperature, high pressure PLT. So before we kick off, as a safety culture in SDI, we start every meeting with a safety moment. So my safety moment today is about the distracted walking. All of us are very connected to our phones, as you know. So we keep looking when we are crossing the roads, or we are going to just grab something from our cars, and probably when we are looking or we put our headsets, we don't pay enough attention to the surrounding environment, and probably there is moving vehicles or objects that can cause serious injury. So my safety tips for today is to maintain volume where you can hear the surrounding, and while you are walking, focus on the people, the objects that moving around you. Also start to alert in mall or other parking lots on other near streets, especially during winter months or when it gets dark. So it's better always to keep your phone in your pocket and pay attention to the surrounding when you are moving in the street. So that's my safety moment for today. For the agenda of the presentation, I just when Mr. Mazen invited me, I thought what's unique that we can bring to the table in this technical discussion. Probably we have a lot of good resources on LinkedIn or websites to read about the case toll logging, and especially the production logging. So I thought what we have done different in SDI to address some challenges. So we have addressed three main challenges. One, the slim MPLT deployment, because we have a slim tools, as I will show you in the next slides. Two, we have logged very high flow rates, which other companies or other service providers were not able to deploy their tools, and I will tell you why, what is the technical reason behind that. Third is the high temperature, high pressure challenges, like above 300-degree F. There is very limited technology in the market, and it becomes very challenging to log those wells. So I'll give you a quick introduction. Why do we need this? Why we are speaking about this in this venue? And then we'll go to the MPLT challenges that I have highlighted, and then we will go to the solutions, which the technology which we can use. And I left case studies at the end so we can compile what we have discussed in as a case studies, and then I left a few slides, a little bit of background about the company that I work for, and open discussion if anyone has a question. So introduction, I believe a lot of people in this call have been in the operator side, or they are working the operator as well. I have started my career in oil field services, so I see things from a different perspective. I have collected some data from technical posts and resources, and this resources, it's mentioned that more than half, about 60 or 70% of the oil production around the globe is coming from a mature field. Why we are saying this? Because this is where we are deploying the PLT. That's where there is a challenge to deploy the production logging on a daily basis or a monthly basis. And from those mature field, 35% is the average recovery factor for the oil fields and 70% for the gas field. So if we are able to enhance the recovery factor by only 1%, that will add additional oil and gas reserves and supply to the world for another two years. So that's for the mature field. For the high temperature, high pressure related challenges, there is a very interesting chart from McKinsey. I'll show you in the next slide that for the midterm, the world will require more 15% of the gas resources. So means that a lot of operators, like national operators and international operators, will spend more money to develop the gas fields, which most of the time possess like deeper wells and high temperature profile. Geothermal energy, it becomes the star of renewable energy. And the good thing for us as oil and gas people, that a lot of technologies that from the oil field services are being used for the geothermal energy exploitation. I would say we as a SDI, we run PLT and multi-finger caliber for geothermal producer on a daily basis in Asia back. So the same tools that we are going to present today, we are using them on logging the geothermal steam producers, and we run multi-finger caliber exactly as any other oil and gas well. So that's the good thing about having the technology from the oil and gas to be deployed and utilized in new energy fields like the geothermal. Right. So as you can see here in this graph from McKinsey and Company, for the midterm till 2031, the gas demand is projected to grow by around 15%. As I have mentioned, that will put like responsibility on the operators to start to invest and drill more gas wells. So why we are saying this here? Because it's related to the high temperature, high pressure challenge that we are discussing for the production logging. We just need to measure how much we are producing, and when those wells are high temp or ultra high temp, it becomes challenging to deploy the BLT on those wells. In this chart as well, I just would like to show you that the geothermal installation forecast is set to increase rapidly for the next like 6 to 5 years, which a lot of countries are running after developing their geothermal resources, and this is also will add additional layer of a challenge by having a reliable high temperature, high pressure BLT tools that can be used for these geothermal wells to be logged and to measure the produced flow rate. So this was a little bit of introduction about how this is related to the topic of this presentation. Now let's go to the technical stuff. So production logging, just like if someone is not aware of this service, why do we run the production logging? We run the production logging mainly to measure the downhole flow rates and compare that with the surface rates that we are producing. And the difference is always revealing any mechanical problems in the well, either a leak, either cross flow, thief zones, whatever is related to the mechanical well problems. And running the PLT continuously will answer three main questions. What do we produce? Which is like, are we producing oil? Are we producing water? And how much? How much is the water cut? How much the oil that we are producing? And where we are producing? Which zone, which reservoir zone that we are producing from? The importance of the BLT will become crucial when we are going to the decline phase. So any field in the world will pass through like three main stages: the build-up, when we are doing the drilling and opening the flow for production. So the wells in this field will start to build up, and then we reach to the plateau, and then we see a decline in the production. The MPLT in the mature field becomes very important in the decline phase. That will tell us a lot of issues that are happening in our wells, like the water production, cross flow, behind casing, channeling, or any related mechanical problems. So we know this data from the BLT, and we can design a proper workover plans, either water shutoff, or adding plugs, or cement squeezing, or reperforate new zones. Of course, this can be combined with saturation logs, so we can identify more zones that need to be perforated, or shut the zones that produce more water. So we can shift the economic limit to additional more years, and that's a lot of fields in the Middle East, either in Iraq or in Saudi Arabia, in Oman, in Egypt. There is a lot of mature fields that have been producing for the past 50 years, applying multiple EOR methodology like water injection or polymer injection or CO2 injection. So this is the importance of the PLT, but it's not always easy. So there is a challenges, as I have mentioned, and I'm going to highlight in this presentation how we can mitigate those challenges. So the challenges in focus is the slim completion, as you probably know, in the mature field, the brown field that we have just highlighted, that the pressure will decrease, the reservoir pressure will decrease, and the support from the reservoir will start to decline, and the fluid velocity to lift the flow up to the surface will be reduced. So the operators will decide, either we use artificial lift method, either ESP, sucker rod pump, and so on, or we can probably use a smaller completion, which is one of them is the velocity string. It's a smaller completion that can increase the velocity of the fluid that we are producing from the reservoir units to be lifted to the surface. So adding a velocity string becomes challenging for the future well intervention like the BLT. The second challenge is the higher flow rate. So we have a very good gas wells in the Middle East that producing up to 150, 130 million scf per day, and it makes it really difficult to deploy PLT or deploy any BHA downhole. This difficulty is from the lift force. So when we are trying to push the tool downhole and the gas production is coming from down to up, it just push the tool to be pounce, and then we need to pull out of hole. The mitigation for that, the usual mitigation for that, is to add more weight bars. So someone is working the operation side in the BLT, he will probably know that. So you need to add more sinker bars, and when adding more sinker bars to balance this force, you need to add more lubricator sections, and you need to bring more or bigger crane to be for the rig up operation, and it will become like a very complex and very heavy operation. The mitigation for that is to use simply a small cross-sectional slick line combined with the MPLT instead of using a wireline PLT, and I will show you why this can impact the lift force resulted for the same flow rate. The third challenge is the high temperature, high pressure downhole environment. So the deep gas reservoir units are commonly high temperature, as mentioned. The requirement for the gas is set to increase by 15% over the next 5 to 10 years. So, and this is add additional layer of a challenge, which is the high temperature. Most of the gas wells that I have seen across the Middle East has a bottom hole temperature above 300 degree F and even more. Like I have seen fields now, they are 360, 380. I have seen some wells in Oman, probably 390. So that's become very challenging when we are running the production logging on those wells. So those are the challenges that are in focus. So how we can mitigate them and how we can address them with the technology. So the first thing is the slim completion challenge. So we can use a slim PLT string. So what we use in SDI is a slim flow tool, which is 1.38, and we have logged some wells in the Middle East with the minimum ID of 1.75 only, so we can deploy the tools easily on those completion, and the performance was very good. This tools is a modular based, so if you would like to make it shorter, we can just break it down. If you would like to deploy the spinner only, the gamma ray, the pressure temperature spinner, gamma ray CCL spinner, so we can plug and play whatever sensors that we would like to be deployed on those wells. It's a slick line deployable, so the slick line is much more cost effective compared to the wireline in terms of the unit, in terms of the number of people per crew that we need, and it becomes more encouraging to the operator to deploy a multi-wells campaign compared to expensive wireline intervention. Extended duration, that's probably addressing the high flow rate, and I will tell you why in the next few slides. The lift force, because we are using a slimmer tool and its memory, and you are using a slick line, so this tool can reduce the lift force by third. we can reduce the lift force by 35% at least for the same pressure or for the same flow rate that we are anticipating. Following the same challenge, the slim completion, in SDI, we use CTS, the continuous spinner. I captured this types of spinner from the book of the cased hole logging from Kappa. They have a very good book. I advise you all to go through it. It covers many topics. Thanks for Nicholas for adding this effort and making it available for everyone. So this picture is from the book. So this is the CTS in the middle, that in the yellow square, right? And it's called continuous spinner, and we prefer to use it in SDI along with other spinner sizes. This is the inline spinner, this is the CTS, this is the full bore collapsible arm spinner, and this is the basket spinner. So what we use is the CTS for the slim completion, and we have small sizes as small as 1.44 up to 3.5. So this is give flexibility to deploy the BLT in minimum ID restrictions. And we can customize these blades. I have a very good slide later on that we can customize these blades with different angle to optimize the response of the flow. Either we are looking through like a low flow profile or a high flow profile. We can always customize and back engineer the spinners to be able to pick the readings for the wells that from the wells that we are logging. Tuning fork density, as you can see, it's a slim in-body single point measurement, makes it also following the slim BHA design that we are using. There is no moving parts, there is no extended parts here and there. It's a completely non-radioactive tool, so it's very safe, and it works on the principle of the tuning fork. So it's a resonating fork, and when we are dumping this tuning fork in a fluid, the frequency is being attenuated with respect to the fluid phase density. So we can measure directly the density for this flow. And here is a comparison between the scientific drilling tuning fork density and the other methods like a pressure gradiometer density, which is measuring delta B and solving the equation of B equal rho GH to calculate the density. So when there is a deviation on the wells, it becomes not straightforward or not a linear equation to calculate the density. In this case, it's more accurate to use acoustic density sensor, and also being non-radioactive, making it very safe, eliminating all HSE hazards to deploy radioactive source in the well. So this is for the slim completion. This is for the slim completion challenge. Just would like to recap for a mature field. For brown field where operators are using a slimmer type of completion or artificial lift or any method that increase the production, but in the same time can make it tight for well intervention. In this case, we use this combo package, which is a smaller CTS, a slim flow 1.38 tool, along with the tuning fork density to get the flow profile in a slim completion wells. The second challenge is the high flow rate. So we have some giant gas fields in the Middle East. I think some of them in Qatar. Qatar has one of the biggest gas fields in the world, and I have seen also some onshore gas fields in Oman, where the production rate is extremely high, and we need to deploy PLT in those wells, and becomes really challenging in terms of rig up and the operational from the operational perspective to deploy the PLT. In this slide, I just would like to show you a comparison for the same wellhead pressure. Like if you are using the 516A line compared to the 0.125 slick line, you can see that using a slimmer or a small cross-sectional area slick line can reduce the lift force. This is the way to balance the force. So for that line, you can see that the force or the force balance really high. You need a lot of weight to add to balance the wellhead pressure to be able to deploy the tool downhole. But for using a slick line, the one here in the blue, you can see that for a wide range of pressures, this is being maintained in the manageable level. So can reduce the lift force by factor of 3. What does that mean? It's very important for the production engineers in this call, and probably you are aware of the vertical lift performance and inflow performance, and you would like to run the BLT in different pressure readings and different flow rate readings, so you can optimize the smoothness and the accuracy of the line that you are plotting to get the accurate operating point, the accurate flow rate operating point. So I was asked by some operators in the Middle East, can we run PLT in 20, 40, 60 million SCAF per day? Because what we do right now, we run it at 20, 30, 40. And this is give us a very narrow range when we are doing the nodal analysis or the IPR or the vertical lift performance analysis, and hence the selective inflow performance that is being highlighted in the technology and in the production engineering and the production technology perspective. So using a smaller cross-sectional area, slick line, the conveyance can make it easier for the operators who would like to run the BLT in a very high flow rate to do the nodal analysis of their field, and also drive the selective inflow performance. So in this slide, this is real cases. This is real numbers from one of the projects that we have done in the Middle East. So each point here is representing one well, all right? So here is the flow rate. You can see here the flow rate in the yellow curve, as you can see, and we were able to log those wells with a very high flow rate can reach up to 130 million SCAF per day, and that's a huge. So that's a huge amount of gas is being produced, and we were able also to stay downhole for more than 150 hours. So Samir, what's the relationship between like the high flow rate and the extended duration downhole? The high profile wells like this, which has I cannot remember the engineering term, but a high production capacity, it takes time. It takes long time to stabilize between each condition to another condition. So if you are starting to log this well with a maximum flow rate, and then you would like to shift to the medium flow rate and the minimum flow rate, the time to stabilize the production between the maximum flow rate to the medium flow rate can reach up to 72 hours and even more. So you would like to have a tool that can stay downhole, like to log the wells with a higher flow rate up to 140 million SCAF per day, and in the same time it can stay downhole 72 hours of a pressure buildup or a stabilization time between each flow condition, and then progressing with the second flow rate, third flow rate, and post shut-in. So we are talking about 150 hours, that probably 7 days. 7 days of keeping the tool hanging on the slick line downhole. So we need to have a very reliable tools downhole to be able to achieve this objective. So we are challenged by the duration, we are challenged by the higher flow rate. So we were able to address those challenges by using customized PLT tools in-house that we have manufactured and developed in SDI. It's multiple spinners, very slim, and it can stay, I think, more than 250 hours. But the maximum that we have logged is 150 hours. So this is how we can mitigate the second challenge, which is the high flow rate in the gas wells. And believe me, this was very beneficial for the petrophysicist. This was very beneficial for the production engineer to give them the flexibility to be able to collect data on a wider spectrum of flow rate and bottom hole pressure. The third challenge is the exciting one, So high pressure, high temperature wells. So just a little bit of background why we are having a high temperature wells. So as this is the SPWLA chapter, so I expect a lot of petrophysicists are joining us. So it's all about the geothermal gradients and the downhole geological events that can increase the bottom hole temperature. So basically, more we drill, the more the more the bottom hole temperature will elevate with a value of 2.92 degrees C per 100 meter. It means that if we will be drilling to around 6,000 meter, we will be reaching to 350 degree F. That's as a simple linear calculation. So it means that with 6,000 meter, which is around 19,000 feet, which is becomes normal in the Middle East now, especially in Kuwait and in Saudi Arabia. It becomes normal drilling, and we can see the bottom hole temperature exceeding 350, 360. But it's not always a linear relationship. There is always downhole geologic events that are happening downhole that will increase or deviate from the linear relationship of the geothermal gradient, and we can see high temperature intervals just shallower than anticipated. Right. Why I'm saying this? Because there is a little bit of confusion in our industry. What is being classified as a high pressure, high temperature? So there is the API classification, the American Petroleum Institute classification, and there is the Oil Field Services Technology Manufacturer classification. So you will see that, okay, we have high temperature tools. So does it mean that it operates above 350 or below 350? So we have ultra high temp tools. So what is this is considered? It's above 400 or so. So I thought to keep this slide as well. So this is as per the EBI classification. This green square here, that's representing the standard temperature envelope, right? And it's below 300 degree F and 150 degree C. Anything above 300 degree F is considered to be high pressure, high temperature. Anything above 400 degree F is considered to be like ultra high pressure temperature, and above 500 degree F is considered to be an extreme high pressure, high temperature. And I have seen that on the geothermal wells and steam injection thermal EOR wells as well. Why we are saying this? Just to show you the size of the challenge or the like the technology challenges that we are having. In the green square, there is a lot of tools manufactured in the market. There are a lot of countries and companies are manufacturing PLT tools, and they are available everywhere. Like anything around 300 degree F or around 300 degree F, you will see like probably 30 or 40 manufacturer of PLT tools in the market. But when we are progressing up and increasing the temperature from 300 degree F above, it becomes limited technology offering, expensive material, critical operation, and fewer number of wells. There was a very exciting statistics I have seen in that SLB, the defining series, that back in 2013, out of 100,000 wells were drilled in that year, only 5% of the 100,000 wells were high pressure, high temperature. It makes it not attractive for the technology companies to manufacture high pressure, high temperature tools, because 95% of the wells are on the green square. So it's better for them to manufacture like standard tools compared to high pressure, high temperature tools. But I have seen over the past 2 years, this has a paradigm shift, and a lot of companies, big companies from the big three and the big four, start to look at investing money and effort to develop high pressure, high temperature downhole measurement tools like PLT and multi-finger caliper and saturation and so on, making it rated up to 400 degree F. SDI, one of those companies that has been pioneering the manufacturing and the technology innovation in the high pressure, high temperature downhole PLT measurement. So we have a Vulcan family tree, which is a production logging system and multi-finger caliber, and we can deploy it either by a memory tool, by memory, by Slickline, or surface readout and memory. That's includes wireline and Slickline and coil tubing. All of those tools, all of the systems that we are having are rated up to 600 degree F. That matches all the envelope of the temperature that we are talking about. So, and this tools also comes on a different sizes. 1.44 makes it one of the slimmest tools in the market. 1.44 is the operating diameter of the high temperature tools that we are using, and we have another bigger system 1.75 and another bigger system 2.25. Mainly, the main difference between these three systems is the flasking, the flask size that we are using. A little bit about the theory of why these tools are different from the standard BLT tools. These tools have two main advantages. One, the materials that we are using, it's a very high graded material, and it's rated up to extreme temperature condition. Second is the heat shield or the flask. It's like the concept of the coffee mug. When you put the coffee inside the mug, it just reduces the heat transfer or the heat conduction between the hot liquid inside the mug and the external temperature. What we do for this high temperature BLT is exactly the same, using heat shielded material, heat shielded, we call it the flask, to slow down the effect of the external temperature condition from the reservoir to reach to the internal component on the tool. But in the same time, the internal component of the tool is high graded materials, manufactured from high graded materials. That's why we can stay downhole in a high temperature condition like 500 degree F or 450 degree F for more than 12 or 14 hours to complete the BLT program that we are having. So this is the theory behind the high temperature production logging tool. It's all about the flask. You have a good flasking system, a good insulation system. You can stay downhole, and also making it smaller. Some other technology companies, they have the same flasking system, but it's bigger. So like the component inside the tool and the flasking system, it makes it bigger. The underlying magic that we are having is to make it smaller, and also to make it rated up to 600 degree F. So we have progressed that not only for the oil and gas, but we have progressed that as well for the geothermal. So we are running, just in case you are not aware of the geothermal wells. Geothermal wells, we are tapping the hot spots downhole and either producing natural steam or injecting water from the same well and producing steam. So we would like to run the PLT in the geothermal wells to measure the flow as well. So we have used the advantage of the tools that we are having, and we have upgraded that to be rated to 650 degree F, and we can run it for 10 hours in geothermal wells. This is the strength of the tool. We have the flow meter, as mentioned. This is CTS, and the good thing about CTS that I just forgot to mention, that you can remove this crossover and you can deploy another tool. So you have a bigger spinner, and it's not inline, and you can deploy multiple spinners on this string. We have the pressure temperature here, we have the gamma ray CCL for correlation, we have the memory, and we have the battery. So we can deploy it by Slickline to collect data about the flow profile in the geothermal wells as well. So that's just to give you some insights about the how this can go, how extreme the temperature can go. So in Asia back, for example, like we have been logging like thousands of wells, the thousands of runs with a high success rate, either geothermal logging or or gas wells, either in Gulf of Thailand, in the Philippines, in Vietnam, in Japan, either geothermal producers or some other wells. We have in the Middle East here a lot of high temperature fields in Oman, in Saudi Arabia, in UAE, and it's growing. And I can tell you that I get requests like on a monthly basis from new operators. Yes, we need to have that high temperature tools to be able to deploy it downhole. So this graph between the temperature and the pressure just show you how things can go like beyond the standard pressure and the standard temperature around the globe. Case studies. So I'll start with this one. So in this case, we have a gas producer that has a source of water, okay, and the bottom hole temperature is 186 degrees C, and we are required to stay downhole for 6 hours as a pressure buildup, and the entire run duration is 20 hours. So this is the challenge that we have. Just in case you are not aware of the PLT logs, let me walk you through this. So the first track is the perforation, okay? Perforation zones. We have 2 zones here, 1 and 2. And the second track here is the spinner, as you can see here. This track is the temperature in degree C from scale 181 to 188. It's very high temperature. Pressure curve, and the acoustic density, and the capacitance sensor. So we can see here that the spinner is responding to that. Most of the production is coming from this interval. However, we have some heating anomaly here that's not pronounced by the spinner. So it means sorry. So it means that there is a sort of a flow or activity behind the casing here that the spinner cannot see. This is probably can be related to behind casing channeling or cross flow and so on. So we can see here that the pressure breakpoints in this pressure curves that responding very well with the temperature curve. We can see here also the difference between different fluids, the TFD. Don't worry about those signals. It's just because when you are taking the acoustic density sensor from different phase to another phase, so there is some droplets of fluid is being like hanged there, and it gives this erratic response. But once you enter the fluid, it just go away, and it just responds very well with the capacitance as well. So this is one of the cases where it was very challenging for the operator to deploy PLT in 186 degrees C for a 20 hours run duration. So thanks to the to advancement in the technology, the 1.75 PLT that we have deployed to collect this data and reveal some problems on this well. The second case here is a gas producer, a tight gas producer, and the bottom hole temperature was 170 degrees C, okay? And they have 2 sets of perforation, one upper perforation and lower perforation. And when we run the PLT, we have identified a downward cross flow, as you can see from the temperature curve. And the second issue was that there is no flow from the lower perforation. So we need to confirm if the lower perforation has a mechanical issue or it's something related to the skin, to the S in the equation. Is it a skin damage? The reservoir is not behaving as anticipated, or the perforation itself is not fully penetrating the casing and the reservoir. So we have run the PLT in this high temperature well. As you can see here, this is the perforation zones, first track, the gamma ray, CCL, cable velocity, pressure curve, temperature curve, TFD, acoustic density curve, and capacitance, spinner 1 and spinner 2. And we can see here some cross flow as you can see here from the shut-in data. Okay, and the operator has advised us to run a multi-finger caliper. So we run a multi-finger caliper, high temperature multi-finger caliper in this well to de-risk the assumption here. So there is two assumptions for the operator. Either is it a skin damage or the perforation has a problem. So just instead of going towards assumption, we run the multi-finger caliper to make sure that the lower perforation is fully opened, as you can see here. Right, it will just come up in the video. Okay, this is the multi-finger caliper run in high temperature environment, and we were able to identify that the lower perforation is fully penetrating the casing, and this has left them with one assumption, which is the skin damage. I remember after that log, they proceeded with the acid stimulation job for the lower perforation, and they have done it, and then we run another PLT after the stimulation job, and we were able to identify a flow profile coming from the upper perforation and the lower perforation, and that's a good thing when you are running the PLT in commingled production wells like in this case. Right, so this case is related to the high flow rate challenge, as I have mentioned earlier. So in this well, we have run three different spinners with three different configuration. So we have run in the lower tool 3-inch 5B. B means the beach angle means the blades either it's declined like this or declined like this. Just the blades angle, and we call it in a beach number. So we have 3B, 5B, 9B up to 20B. The smaller the number, if I recall correctly, means that higher RBS. So you need to design your spinner correctly to get the maximum identification or detection of the flow that you are looking. And sometimes you don't have to use like a very low B, because in a high flow rate profile, because it will just keep rotating and it will not give you a deflection of the reading. So in this case, we have deployed three types of spinners in the same tool, in the same well, in the same condition, and we can see here that this is the gamma ray, this is the temperature curve, this is the TFT, and this is the three different spinner in the same tool, spinner 1, spinner 2, spinner 3, and we can see very good repeatability, which is like I would say gives a lot of value to the logs that you are running. Instead of just running one spinner and inline spinner, we have run like three big spinners. There was 3-inch, 3.5, 3.5, three CTS in one PHA. So that's give a lot of like luxury to the petrophysicists to choose what is the best data set that we need to have for a further data interpretation. Another case here, this is a cold tubing. It's a block setting, depth correlation, just a very simple job. But the challenge here is that this is a horizontal well, 6,000 meter and 200 degrees C, extreme condition. When you are using coil tubing, you have a slow logging speed. So this is add another layer of challenge. A slower logging speed, run in hole and pull out of hole makes the exposure longer. So you need really a reliable tool that can be deployed downhole for this condition. So we have introduced to that operator the 2.25 system, and we have tested our tool in maximum temperature up to 232 degrees C in the oven, just to make sure that we are covered. And we have deployed dual string. That's also another advantage of having a memory tool, that you can combine multiple tools together and you can deploy them. And here in this graph, just would like to show you, this is the temperature. Okay, that's the temperature on the vertical axis. The blue curve here is the external temperature, the reservoir temperature in the well, and this is the yellow curve here is the internal temperature of our tool. This is just to show you that even in extreme temperature conditions above 200 till 232 or 240, our flasking system, our heat shield, has maintained the internal temperature of the tool below 150 degree C, which is the normal operating envelope for all the circuits and all boards inside the BLT string. So this is a dual challenge: cold tubing, slow logging speed, ultra high temperature, and we need to finish the correlation job in the assigned time. So we have used the Vulcan flow logging system, FLS flow logging system 2.25 for this application. Right, so I have done with my technical part. I just kept 2 slides here of just a little bit of background about SDI. So we are offering cased hole services since 1982. We were able to develop the one of the first like high temperature memory gauges back in 1983. Rated up to 600 degree F, and then we have kept developing our ultra high temperature capability since then till we introduced the first commercial geothermal multi-finger caliber 40 arm that has been used extensively in the geothermal market, and we are keeping developing and researching how to make it more reliable and how to extend the time downhole for when we are using our high temperature, high pressure PLT. We have worked with multiple operators around the world, and this has given us a lot of learning lessons that I would like to share, that I shared with you already today, and there are many more. It's good to be in the oil field service part because it gives really a good chance to expose to multiple scenarios and multiple operation requirement that we need to address and mitigate. Okay, that's my last slide. Thank you very much. That's my email. If you would like to get more information about these tools or these cases, please drop me a line. You can scan this QR code to connect with me on the LinkedIn. We can exchange ideas and probably we share technical discussions here and there. Thank you very much, and going back to you, Mr. Mazen. Right, probably he's not around. So guys, feel free to step in, type your questions on the chat box, or just open your mic and ask the question. So yeah.
Mr. Samir Mustafa, I'm here. I'm Muhammad Jawad. So any person who has any question, he can ask Mr. Mustafa, or can he write in the meeting chat, please. Mr. Samir, there is a note for you. You can read it, please. Vulcan PL system, was it not a 1.38-inch tool that you mentioned in the presentation earlier on? Vulcan is slightly bigger in diameter tool. What do you say, please?
Yes, Mr. Shahid, thank you for your question. So we have two different systems. We have the standard PLT system, which is 1.38. That's a standard PLT. That's a completely different tool. Okay, and it's 1.38, the operating diameter. And for the high temperature, ultra high temperature conditions, we have three different systems, which starts from 1.44 1.75, 2.25. So for the slim PLT standard temperature condition, we have the 1.38, and for the high temperature conditions, we have the 1.44, 1.75, and 2.25. Okay, thank you.
Okay, Mr. Samir. Vulkan PLT is more advanced than normal PLT. What is the difference? Also, MFC is more advanced than normal caliper.
All right, Mr. Ali. So it's not about the advancement; it's about increasing the operational capability. So it's the same sensor, Mr. Ali. So you have the spinner, you have the pressure, temperature, gamma ray, CCL, acoustic density, and capacitance. So it's the same sensors, but instead of limiting the deployment of this tool till 300 degree F, we are increasing the operational envelope up to 600 degree F. So no major advancement on the sensors, but increasing the operational capability of this tool to be deployed in extreme conditions. For the multi-finger caliber, the second part of your question, the advancement in the multi-finger caliber also the same. The normal caliber in the market are rated up to 300 degree F or 350. Our multi-finger caliber is rated up to 428 degree F. And that's gives the tool the advancement in the gas deployment and high temperature condition. It's the same concept, same data, but we are increasing the operational envelope. Think about it. If you have a phone and instead of using it underwater for 1 meter, you are using the same phone like 10 meters down water, like below the water level, or using it like 30 meters below the water level. It's still the same phone, same function, but we are adding more capabilities and more specs to that phone.
Yes, so thank you, Mr. Samir. Actually, I was hearing you, but I like faced
Okay.
some technical problem, so I need to restart my PC. Okay. Thankfully, the recording wasn't deleted. Um,
Mm.
so I believe Dr. Muhammad, I was hearing Dr. Muhammad interfere also.
Yes,
Okay.
yes.
Yes, yes.
Yes, Mr. Mazen.
Okay, this is great. So I'm not sure there was several answer on the chat. It's several questions on the chat. Okay.
Yeah, I think I have addressed them all. If
thank you.
if they are more, I'm happy to hear. Yeah.
Yes, from my side, it was really informative webinar. It is like in my domain, okay. And this case study is really interesting to have such tool in very hostile environment, okay. If there is no more question, actually, I have some few questions, if you don't mind.
Yes.
So for
Please.
this small spinner 138. Usually, the blade size, I believe, is not that much. It will not cover all the well bore. So, for gas well, what will be the correction factor as per experience?
Okay. It's still like it's not. I agree with you. It will not cover the entire the entire casing circumference, but you are asking yourself a question. I should have data or like having data or perfect data. So the question for the operator, they don't have any. Yes, yes. So when they have an ID of 1.75, they are asking the question: should we have the perfect data with full bore spinner? Of course, the bigger the if the spinner bigger, it means it's better response. When you are deploying the full bore spinner and 7-inch casing, it will be always good. When you are deploying it in 5-inch liner, it will be always good. But sometimes, in some cases, you are challenged by minimum IDs like 1.65, 1.7. So the operator is not able actually to deploy the BLT tool downhole. So what we do is we use CTS as small as possible to pass through the minimum restriction, and as big as possible to collect the data. For example, you have 1.75 minimum ID and you have 7-inch casing. In this case, I will go for something like 1.5 or 1.44, because this is the available size. Let's say we have 2-inch minimum ID. In this case, I probably will go for 1.75 or 1.85. Depends on the availability of the spinners that we are having and designs that we are having. So we are comparing, Mr. Mazen, the question of having data with no data. That's one. The second, in the gas wells, I don't really understand what is the correction. We just like if you're speaking about
like when you have like a
the
turbulent or laminar flow, okay, and to correct the apparent velocity, okay, usually you multiply it by 0.83, okay.
okay,
So I'm not sure for gas well what is the correction factor. If you remember this in the theory, like when like it is included in the interpretation, okay.
yeah,
Because when you have laminar flow, you want to the velocity in the middle is very high, and the spinner usually measure in the middle. So you want to reduce the average velocity, okay. So you reduce it a little bit by multiply by 0.83 on average, okay. This is in the theory, but for sure in the interpretation program
yeah.
will be a regression, fully different story. If you don't
Yeah.
have this one, it's okay. There is no problem. Okay.
Yeah, I wish I can answer this. It has been some time since I handled the software and interpretation.
Okay.
I totally agree with you. In some laminar fluid and turbulent fluid, it's different. But I don't recall the numbers or the
It's
correction, to
okay.
be honest, Mr. Mazen.
It's okay.
Mm-hmm.
It's okay. No problem. For case study one, okay, I believe
Mm-hmm.
this is a flow inside wellbore, but it's below the spinner threshold. Okay. The
Mm-hmm.
case one. Okay.
Okay, let me grab this.
It's always interesting to discuss this PLT case studies.
Mm-hmm.
Okay. Okay.
Yeah.
So yes, with this one, because if it is behind the casing, that will be only the temperature will be affected. But this one is
Mm-hmm.
inside the wellbore, and you can see that there's a deflection in pressure, there is a deflection in density tool, not only the temperature. So this indicating this event is sensing inside the wellbore. It's happening, and it's have been sensed by many tools, except the spinner, because apparently this is a low flow rate entry
Mm.
in this one. Okay.
Yeah. Yeah.
Yeah.
Yeah, that's correct. I agree with you on this. Like I can't remember what happening here, but
There is a flow.
the spinner is not. Yeah, there is a flow, but if this flow probably is getting into the
A little
cement
bit.
and being produced from here, I think your assumption and your point of view relying on the pressure curve and the TFD, the entry points, which is correct, but it's still like this is can be something on the sump, so there is some stagnant flow into the sump, and
This
it
one,
might get change. Yeah, the
uh,
sump from here downward.
maybe, but I will tend more there is a low flow rate of very light
Mm,
thing.
yeah,
Okay, we see this
yeah.
case study a lot of this, and for
Hmm.
this case study two, I believe this is flowing, and they saw this like the next slide. Okay, if you go to the next slide, okay.
Okay.
I believe this is flowing condition, but the shutdown you are referring to wasn't presented here. Okay.
No, it's actually this is the shutting condition, if I'm not mistaken, because here we measure always the cross flow in the shutting condition.
I know, I understand this
I
one.
think this is
Okay.
this. Yeah. Mm-hmm.
But because if this one will be on shutting condition, so that means the zone above the perf okay, it will be parallel on 0. Okay, you can see it is shifted to the right side toward the 20. Okay, it will be in similar way to the zone, the most deepest zone.
Mm.
It will be shifted to the right side. Okay, and the cross flow will be tight in the middle. You know, like it will go like it's parallel to 0, go to the right side, then it's parallel to 0.
Mm-hmm.
Left side parallel to 0 again.
Okay.
You can work about it.
It was, yeah,
Unless it's
it's a
producing,
good catch.
unless it's producing to
It-
the surface. I don't know. Unless it's producing something and the well is shutting and the
Mhm.
cross flow is upward somewhere.
Yeah, we relied on to assume this cross flow, like we assume that based on the temperature, as you can see here, the temperature curve can clearly show that, and also we have the spinner response from spinner 1, spinner 2. So it's either a production from the lower perf, because Mr. Mazen, it might be different layers, you know, different pressure layers. It's just not a very homogeneous reservoir unit, you know. So probably there is differential pressure from this unit to other unit, and the fluid is going from one unit and being produced by another unit. So this is the whole point of the cross flow. Your point of view is right. If we are looking at if you are looking at this reservoir zone as one uniform homogeneous unit, but I believe in this well there was multiple layers with different pressures.
Okay, no problem. And for
Mhm,
the third case, okay, and for
mhm.
the third case, uh, just a question. I believe the spinner number 3 have the best or the lowest threshold, if I'm not wrong. Just the outcome of this test. You figure out the number 3 because I
The
can see SP3 because it's giving a
mhm,
very high response round per second.
mm, yeah,
I believe it's a
yeah.
very light spinner.
Yes, it's also like the difference in the impeller. Like this is helical and this is pedal impeller. This is 30 degree, so it has different configuration. So that's why we have tried multiple spinner to choose which one has the best response. So it looks like that the middle tool and the upper tool has the excellent response in the gas. So we have normalized that in our operation. So the objective of this case is to deploy 3 different spinner with 3 different configuration to be able to capture which one has the best response in this condition.
Okay, thank you. Uh,
Mhm.
I have no more question. I don't believe I saw just one chat, something in the attendees. Somebody asked a question. Okay, and let's conclude the webinar with this question. For laminar flow correction factor is 0.5. Okay, he sent the photo that I was talking about.
Mhm.
Like they say, environment friendly, operate friendly tool, basically. Okay.
Thanks,
Don't,
thanks, Jose. Yeah.
yes.
Just guys, the last time I had I was using a software was like 9 years ago. I'm in the business development side now, so but I started as a will log analyst. So excuse me if I forget a little bit of information
Yes,
about
it's okay.
the processing and interpretation.
Yeah, actually, the goal of this series of webinar is not to focus on software or interpretation. Actually, the main goal is to show the tool itself, the manufacturer. Okay, not only the software. There will be next webinar will be on
Yeah.
software with Kappa, and I believe people can join and ask Nicholas as much
Mhm.
questions they like on
Yeah.
these tiny things in
Yeah.
the software. Okay, but the main goal is to have variety of webinar. Some on
Yes. Yeah.
tools and some on,
Operational data.
yes,
Exactly.
operational.
Hmm.
Exactly. Okay, and let's conclude. I believe no more question. Thanks
Yeah.
for your time, Mr. Samir.
Sure.
Oh, okay, and
Thank you.
it was much appreciated webinar, formative.
Yeah.
Any last word, Dr. Mohammed?
Thank you, Mr. Samir, about your great webinar today. We would like to continue with you really about your interested webinars next time too. Thank you for everybody who attended to this webinar. We hope to maximize our job with you and with other lectures to expand SPWLA work in the Iraq. Thank you, everybody. Thank you, Mr. Mas.
Yeah, thank you, Dr. Mohammed. Just one last thing. I saw many people asking if can this presentation shareable. If not shareable, it's okay. They can watch the video, but if you can share it or not, I'm not sure. If you cannot, it's okay.
I can just remove a couple of things and I can send you a PDF. That would be better. Yeah, it's shareable, no problem.
Okay, thank you so much.
Yeah.
Thank you, Mr.
Okay.
Samir.
All right.
Thanks for all attendees, and see you next month.
Okay, thank you, guys.
Thank you.
Thank you.
Bye
Bye.
bye. Have a
Thank
great
you.
day
Bye.
all.
Bye.